Hi, I'm fascinated by the attention mechanism in transformer. Here is my journey. So the problem that I can see is if you search deep neural network, you find many pictures like this where you have some lines and some nodes and lines. And if you try to learn deep neural network, this is relatively easy to understand, and we use input and output and backpropagation to train the weights. And then if you search attention transformer, you get something like this, where the focus is matrix multiplications. And if you say attention and deep neural, it's no help here. So we have deep neural network, which is relatively easy to understand, which use lines and nodes, and attention transformer use matrix multiplication. So there's a missing link. Why is there no drawing of the attention mechanism added to a DNN, deep neural net? What are we missing if we jump here? And there are many good videos about this. I'm not criticizing this, but how can you add attention to this? That's what I'm trying to look at. So the attention approach, difficult but also exciting, and we see something that is not easy to see with the matrix approach. So when we use this DNN approach, we can see something new. Okay, at least it was new for me. So the paper "Attention is All You Need" started all this, and there was a author like Ashish Vashvani, don't know how to say it, something like that. And this is the guy. He has a very good video on YouTube, and I think there is 3 videos, different videos, where he explains very much the same. And he has this picture, self-attention. It's a very nice picture. And then he has a second image too, which is the same, but added some key queries and some softmax. So this is the simpler, and this is the more advanced. Okay, so let's start with the simple version first. What's happening here? Okay, now I put the image down here. So in this example, we have a cat, a dog, and car, and they are embeddings. That's what they call here, embedding. In this example, there are 4 embeddings. I have only 3. And embeddings are just numbers. And in the real transformer, there are more than 3 values. There are hundreds for every word. Okay, but just to keep it simple. And then it says that we are now looking at the number 2 embeddings here. We should compare it with 1, and we should pair it with the 3, and should compare it with the 4. Actually, we should also compare it with itself, but it's not visible here. Okay, so how do we do that? How do we compare here? What's that? Well, it's pretty simple. Oops, sorry. You take the values 1, 1, and 3 and make just a copy up here, and we call that the query. That's just a name. And then we make another copy. Okay, 3, 1, 1, and we call that the key. Okay, so now we have 3 copies of the same. And then now come the smart. We do this. We multiply 3 by 3 and put it here. That's 9. 1 times 1 is 1. Now we have 10, and 1 and 1 is 1, and we have 11. So we take this, multiply by this, and get 11. Well, what's happening here? Well, you have 3 inputs and 1 output. And what is this? If this is in and this is out, what is this? Well, let's look at a fully connected neural network. In our sample, we have 3 and 1. It's this one. We could have 1 to 3, 3 to 1, or 3 to 3. Of course, because I have 1 to 4 and 5 and all that. But okay, you can see 1 to many, or many to 1, or many to many. what is this line here? In a normal deep neural net, what is this line? Well, it looks like this. 2 is coming in, and 4 is getting out here, and 10 and 6. That doesn't make sense. Well, that's because we are missing the weights. So normally when we draw, we don't draw the weights here, but there are weights in this line. Okay. So if you say 2 times 2, that's 4. 2 times 5 is 10, and 2 times 3 is 6. And here you have the code doing exactly the same. And then another sample, 2 times 5 is 10, and 3.4 is 12. So now we have 22, and 4 by 2 is 8, so we have 30 together. So we sum it up here. And the same is here, 2 by 2, 5, 3. We sum it everything up. We're going to look at that later. I think you get the point. So every line in a fully connected layer has weights. And what can we say about these weights? Well, we can say that these weights are just changed when we are training the network. So when we are finished training the network and we are going to use the network, okay? So we add 2, 3, and 4 in, and we get this out. We can next time we could put 5 and 7 and 11 here. We get something else out. But these weights will not change. The input and output may change, but the weights are not changing after we are trained. So we call that slow weights. Okay, that's important because these are not slow weights. You can see them as fast weights because they change not after training but by the input. Okay, so imagine we are now using the network. We are adding cat 113 in, and we get something out. And next time maybe we put a doc here, 221, and these will be changed, and this one. These will change. So these fast weights may change for every time we call the network or use the network, not when training. So they are fast weights. So this means that the system is extremely dynamic. It changes its behavior by the input itself. Okay, this is not going to change the weights by the inputs. Just these weights are frozen, if you can say it like that. These weights are dynamic, depending on the input. So this is one of the main idea behind attention. That's not easy to see when only using matrix multiplication. Okay, so we know now that 11 here. So what's this number mean? Well, this means that cat believes that cat is 11 word. So I'm gonna focus 11 on myself. Okay. And okay, so we know cat is 11. So what next? Well, we take the key for the dog. The key is just 221, 221. And what do we do then? We take the query again as the cat query, and 3 times 1 is 3, 1 by 2 is 5, 1 by 2 is 7. This means that the cat thinks that the dog is worth 7, has the weight of 7. Okay, the cat thinks now that itself is 11 and the dog is 7. Okay? And the last, we take the key from car, which is -2, -1, -2. Here, just a copy. And we, of course, use the query again. 3 minus 2 is -6. 6 and 1 and -1 is -2. 7, sorry. And -2 is -9. Okay, so everything is the focus from the cat now. So the cat thinks that it is 11 important, and it thinks that the dog is 7 important, and that the car is -9 important. So say it like that. Does it make sense? Yes, it do. Because cat is 113 and dog is 221, and the car is -2, -1, -2. So car is absolutely not similar to these two. And that's what we see here. Okay, so what's next? Well, now we have the importance of all the 3 words here, and then we take the value, copy again, 113, 113, and now we have to use this to we use it to make the dot product. So 11 times 1 is 11, 11.1 is 11, 11.3 is 33. So now we have a new vector. So this one is now become 11, 11, 33. So it is, you can say it becomes 11 times bigger. Okay, the original is now 11 more here. Okay, then we have to do the same. This is fast weights again. So now we have 1 and 3. Before we had 3 to 1, now we have 1 to 3. So again we have fast weights here. So we have 2 times fast weights. So it's very dynamic system. Okay, now we take the value from the dog, which is 2 to 1, and we of course multiply it by 7 because the importance is 7. 7.2 is 14. So now dog is become 14, 14, and 7. Yes. You have to remember it's the cat's meaning of the dog. It's not the dog's meaning. We are still focusing on the cat. Okay? So the cat think that the dog is 14, 14, 7, and it itself is 11, 11, 33. And now we have to figure out what the cat thinks about the car. We take minus 9 here, and we times minus 2 is 18, 9, and 18. So now we know what all the vectors, the 3 vectors for all inputs, and it's still the cat's meaning. And then the last step, we're going to add them together. Take them 11, add then 14 plus 11, 25, and then 18. So we plus, get 43. This is a strange thing. We simply take all the vectors. You can see we take all the words and just make it to one word. So now this word, as the cat, has the word dog and car inside of it. It's a little bit strange that you can do that. But that's what's happening. And now we have a new vector which includes the entire sentence. Just for the cat. This is cat's meaning of the entire sentence. Looking from the cat. And then we can just put a new forward network, a deep network here if you want. That's this one. Okay. And now we do everything again, but now we are going to focus from dog perspective. Now dog is going to look at the cat, and it is going to use its query here. And again, and it's going to say 7, and it takes the key from itself and look at itself. It's going to give it 9, and the car, which is minus 8, which is again, dog is more similar to cat and not car, which we can see here. And now again we take 7, I take the value, and we get a new vector 7, 7, 21. Remember, it's the dog's meaning of the cat value here. And here we have the dog meaning as 9 points this to itself, and at last we get the dog's meaning of the car. Okay, and then we sum them up. 7 plus 18 here is 25, and 16 is 41. Now this vector is the dog's meaning of the entire sentence. Now we have 2 words. We have the cat's entire meaning of the entire sentence. We have the dog entire meaning of the entire sentence seen from its perspective. And now we are missing the car. Do the same. Query the car. And key from the cat. Minus 9. Then is the key. Is still the query and the key from the dog. Do the same. Minus 8. And at last, the car will think itself is really important. It's 9, and the other ones are not important. Minus and minus. That makes sense. Again, car does not look like dog and cat, so everything is fine. And then we have to use the value, and we get minus 9, minus 9, minus 27, seen from the car. And again, from the dog, minus 16, and from the car itself is this one. Okay, and then we sum them up, And now we see that the car's meaning of itself and the entire sentence is minus 43, and that's it. That's the attention. We have now 3 new vectors that includes the entire text 3 times, if we can say it like that. Okay, so here we have the C# code for exactly the same. And there we have the calculation. You can see there are matrices all over the place here. And what is this happening here? You can see that the cat is of course 113 here, and it's everywhere. And now I have taken the 3 steps and put them together. And in the transformer, it's very important to note that these 3 steps, also the cat perspective, the dog perspective, and the car perspective, they can run in parallel. That's one of the most important strengths of the transformer. If you use the RNN, you will have to run this first, and then this, and then this. So very slow, but it's been made so that it can run in parallel. Okay. So what do we see here? We see the cat there, okay? The compatible score, okay? 11, 7, minus 9. 11, 7, minus 9. Okay, so the first row is the cat's perspective, and the second row is the dog's perspective, 7, 9, minus 8, 7, 9, minus 8, and the car perspective, minus 9, minus 8, 9, which is this one. Then this is going to be used to calculate the weighted embedded. So we get 11, 11, 13, 33, 11, 11, 33, 14, 14, 7, 14, 47, and 18, 9, 18. So this vector matrix is now this here. Okay, and this here, the dog perspective of all the words, is this matrix here. 7, 7, 21, 7, 7, 21, 18, 89, and 16, 8, 16. This one. And the same for from the car perspective, you have minus 9, minus 9, minus 27. This is this one. 16, 16, 8, this one. And 18, 9, 18, this one. And the entire output is 43, 34, 58, this one. And 41, 33, 46, this one. And the last one is minus 43 and minus 34 and 53, this one. Okay. Now we are going to look at the more advanced version. So this is the version we have just finished. And this is the more advanced. There are coming something extra here. The key and query. You know, we used the name key and query, but in the previous it was just a name. But what are they doing? Well, they are matrices here. Okay, and the value is also a matrix. What does that mean? Why is the matrix there? It does exactly the same, just this extra here. And there's then softmax. We're going to look at what softmax is doing. But it's exactly the same. There's then softmax level here, which are just here. Okay, and there is this matrix multiplication here. Okay, let's look at it again. We have the image here. Now, you remember we had the cat and that the query was just 113, but that's not the real what's really happening. There is actually a network here. Okay, a 3 times 3 network, and there are weights here. There are 9 weights. Okay, I have also added it here, just so do you remember it. So this value 113 is absolutely not gonna be 113 after they run through this network, okay? But I just keep 113 here, but they're gonna be something else. And these weights are trained by the network, okay? And this is the example again. So this is exactly the same as this. 3 input, 3 output, and these weights are trained, okay? So these weights are not fast weights. These are slow weights. These are the only weights that are trained. Okay, so we go down and we make the key, And the key is also, you see, key is also a matrix multiplication here. And again, there will not be 3, 1, 1 out of here. There will be something else. And then I get the network up here also. So we have two networks here. And then we do exactly the same. And we do, there's no change here. We have a value. And remember, next time we use the doc key here. Remember, it's the same network. So the key network that was used here is exactly the same that used here. We use exactly the same weights as we did here. Okay, so there is only one key network which we're using all the time. So if we have 100 words, we're going to use the same network 100 times to find the key. Okay, and then we do the same. Query goes in, and then you already know that. And the key, again, vector here, is again using the same network. So we have used this network 3 times now. And then we come to the softmax. And what is softmax? Yes, softmax is helping the system. You see the softmax here. It's helping the system so that the value is not exploding. These values are too big, so they make everything. If you add every number together, so 0.98, 0.02, and 0.0, they come up to 1. Okay? That's what softmax do. We call it, sometimes we call it probabilities. So 11 is much higher than this one. This is a little bit strange that 11 is much more than 7, but you have to look at that to -9. Okay, and then you have the value, and again the value is also at network, a matrix of 9 values, 3.3, and this value is of course not going to be 1, 1, 3. They're going to be something else again. And then we do exactly the same, and we use the same value here again. Yeah, there's nothing new here. Okay. And next time you take the query of the doc, and again you use this network. So when you are really working the transformer, you are using 3 networks. Okay, these are the same network used every time, and this network that is trained. Okay, so it's gonna be better and better and better. Okay, so let's see the last example of what is actually going on here. So here we have an input 213 and we have 432. We're gonna look at this 213, this one, and we have 432. Okay, they are going to do something with that. Okay, we have the weight matrix here. This is the matrix. So this is this matrix. Okay, it was the key matrix, key, and we have the query matrix here. So this is the query, and this is the key matrix. You see, they are here. They are numbers. Those numbers are gonna be trained. This here, weight this is weight key, weight query. Now we have to multiply this value with this weights, and then we say 213 multiplied by this one is gonna give us, when you multiply this through, we're gonna get this keys 3, 2, 1. Okay. Yeah. So you can see the calculation down here. You say 2 times 909, 1 times 06, and 3 times 03 gives us 3.3, which is this value. Then we move it to this place, 2 times 08, 1 times 05, this one, and 3 times 02, give us 2.7, this one, and then last we go to this area, and we get 2.1, okay? And then we do exactly the same with the query. 432, the query here gives us 3, and then we move it here, we get 309, and then last we move here, 409. So now then we dot this together, this one with this one. So it says 3, 3 times 3 gives 909. 2, 7 and 3.9 here, 10, and 22.1 and 4.8 gives us 10. And then we add them together, get one value, and there's also one small trick. They divide it by 3. It's because it's the, I don't remember if it is the size of this, or yeah, it's the size of the vector. Yeah, it's 3. That's just a technique they use to again stop the values for exploding. Okay, so we did not divide it by 3 in the previous example, the simple example. This is just extra we do. And now we have a value of 17 here. This is 17 now, and we add it here. Okay, so now this, the embedding 2, it has a belief of embedding 1 to be 17. Okay. Okay, so this is the value here. Then we softmax it. So now we have the entire matrix here after we're doing everything. And when we softmax it, we get this value, 0 and all the, you can see much smaller values. And now again, if we would like, now we are looking at the value here. If we have this value, okay, and we have to find the value of the softmax, we multiply it by these values here. And then this will give us the value of 2.12. Okay, and then we take this again and multiply it by this one, and then we give 2.3, and again this one, and we get 3.7 for the first word. Okay. So this is how it's real made in the transformer according to this image. Of course, in the real transformer there are multiple of these and everything that's more complex. And the embeddings, we have not talked about how they calculate, how they get the embeddings. That's also a network, just getting them embedded. But I have not talked about that here. So now I think we have a good understanding of how extremely dynamic the system is with the slow and fast weights and the matrix, weight matrix, which are put in here. But remember, the key metric here is been used for every calculation, and the query, this metric is used for every query, and the value again is also for every value. So there are 3 weights matrices for the entire system. Thank you.